Hello everyone, and welcome to the Season 2, Episode 8 of the OpenHW TV. Here we are today with Jerome Quevremont from Thales, Tariq Kurd from Huawei, and let's welcome for the first time Mark Himelstein from RISC-V. So today we are going to talk about a new topic, which is the RISC-V profiles. We are going to hear from our guests what we think of, and as usual, we pre-recorded some video content. It's about 30 minutes of pre-recorded video for improving the user video and audio experience. So during the pre-recording session, we will be here listening to that together with you, and you will be typing your questions in the Q&A session, and we will be replying to those questions at the end of the live session, so at the end of in about 30 minutes. So we will be back and replying your questions. So I encourage you to type them, and so nothing to add from here on. So enjoy your video and see you soon. Welcome everybody to the episode 8, Season 2 of the OpenHW TV. I'm Davide Schiavone, and today I'm going to give you an introduction of the OpenHW Group and this episode overview. We're going to listen to Mark, who is going to talk about the RISC-V profiles, which are specification of the firmware and hardware for a RISC-V platform. Then Jerome is giving us an introduction of the CORE-V course roadmap and how they map to the RISC-V profiles that Mark just described. And finally, Tariq from Huawei will give us an introduction of the CV32E41P OpenHW Group CORE-V IP and a dive in the ZTE extensions draft of the RISC-V. At the end of this episode, we will have a Q&A session where all of us are going to reply to the question you will be writing during this episode. So the OpenHW Group is a non-for-profit company based in Canada. We have a global footprint with the developers in North America, Europe, and Asia. The OpenHW Group is driven by its members, so the members decide the project we work on. And what we do is providing an ecosystem for developing open source hardware IPs and related software and tools projects. We also give support to our members, and actually all the IPs we develop, I have permissive license, and they are freely available to everyone. Currently, the OpenHW Group has more than 74 members and partners. We have members from all around the globe. Most of them are companies, and what the companies do is engaging with the OpenHW Group to develop open source hardware together with other companies in a collaborative manner. And together with companies members, we also have a good group of academics partners. They are both universities and research institutions, and what they do is using the OpenHW IPs that we develop for their research projects. Finally, we also have partners, and they help us maintaining and developing and improving the OpenHW ecosystem. The OpenHW Group is organized in working groups, and working groups are split in task groups. So the working groups are actually the technical working group and the marketing working group. The technical working group has a chair and vice chair, and it's defining all the technical activities that OpenHW works on. And it's separated in task groups, and in each task group, we actually do either design of open source hardware, and this will be the core task group, or we verify those IPs, and that happens in the verification task group. Then we also have a software task group that cares about operating system, compilers, and tools for the open source hardware that we develop. And the hardware task group cares about microcontrollers, peripherals, and all the IPs that surround the CPUs. Then we also have the marketing working group, where dissemination and exploitation takes place, with the university outreach task group, where we have research collaborations between universities and Canadian universities. Alongside the working groups that I just described, you also have regional working groups that are in definition right now. Those are the Europe working group and the Asian working group. Those working groups actually focus on the technology and strategic requirements of those regions, implementing digital sovereignty, participating to regional projects, and carry out marketing activities that are focused on Europe and Asia, respectively. So thanks a lot for listening to my introduction. Now we listen from Mark about the RISC-V profiles, and let's welcome Mark and see you later.
Thanks, Davide. I want to introduce myself. I'm Mark Himelstein, the CTO for RISC-V, and I'm here to talk about profiles. First thing we're going to talk about is what profiles are. Profiles are very similar to other architectures where they either have a version number or a product name, where they have a group of instructions that work together. This is the similar thing for RISC-V. We haven't had this up until now. This is a big deal, and I'll go through why it's a big deal and why we care about it. So profiles are a mechanism to identify a group of extensions, which are instructions, behavior, and state that work together. So in our case, you'll have something, for example, for the things that we ratified in 2019, and they'll be grouped together. Why do we care? Because we ask the upstream projects, the compilers, the operating systems, to target these profiles and not target anything else. Otherwise, they would be asked by 100 people to do 100 different things. This is the way we reduce fragmentation in the RISC-V community. The number one question I get asked about by interviewers and other folks is, how do you stop fragmentation? Well, we stop fragmentation by, first of all, telling everybody where they ought to be going. And that's what profiles are about. But the second thing is we are striving to reduce duplication. That's why we have a community at all. So we get to share things that have been done a lot before. If somebody has something that's added value, they do their own thing. So we have a little saying, we say, don't duplicate, innovate. The ecosystem that I was talking about, that we tell about these profiles, is on this slide. And you can see in the middle is the RISC-V ISA with architecture tests and formal models. Above it is the whole software stack, and you should be very familiar with those pieces. Those are the pieces we tell about these profiles. Go for these profiles. The compiler flag should have these profiles. The tools on the left target these profiles. The stuff on the right, just so you know, those are attributes. Everything has to be secure, performant. And the stuff underneath are things that are machine dependent, implementation dependent. And we don't do those inside of RISC-V. We rely on partners like Open Hardware to do those things, or proprietary implementations. There are a bunch of dispositions for instructions. So there's M for mandatory, U for unsupported, optional, S for supported optional, I for incompatible, X for not ratified. And there's one that's not on here called N, which is basically that it's not applicable. So what does this mean? So M mandatory, pretty obvious. Supported optional means that if it's there, the operating system, for example, has to do context switch. A good example of this is vector. It has vector registers. If it's around, the operating system has to save and restore them. Unsupported optional means that an implementer is on their own and they have to do it themselves. Incompatible is like ZFNX, our floating point in integer register extension. If you have that, you can't obviously have the normal floating point, which has floating point values in floating point registers. They are incompatible. And then the other two are pretty obvious. So I just want to hop right into examples. So there's 3 examples here, and they're based on year and type. The first one's a grandfather one, RVI 20. Anybody who did something before we had profiles, they get to say they're compatible with that. RVM20 is the microcontroller or bare bones, simple RTOS kind of profile. And RVA is for like a rich operating system application layer. We also allow you to have compatibility dependent on mode. So there's a certain set of extensions that work at M mode, at S mode, system mode, and U mode, which is the application mode. I will apologize that M is used in two places here, both as a type, microcontroller, and M for M mode. And it may be a little confusing, but that's why we have this picture here. Hopefully it makes it easy. And then finally, we have size. So 32-bit and 64-bit, this refers to the width of the registers. And we support 32-bit both for the grandfather and for the microcontroller profile. But right now, we don't support it for the application profile. We can revisit that if there's great interest in it. As you can see, there's the basic stuff that sits in RVI. Some things are supported optional. And then when you go on to the RVM, we add some of the priv instructions that were there as optional become mandatory. But for the U mode, it stays the same. And then let's go to RVA. And RVA, all of a sudden, a bunch of the things that were optional in the base stuff in RVI 20 become mandatory. And that's important because what we're trying to do is evolve things and move things forward. The rules are pretty simple. I'm not going to really go through these in detail. The application layer, Linux class kind of stuff for this profiles, microcontroller, again, cost sensitive base stuff. We're going to release profiles once a year. And the whole idea in the end is you should be able to run the same sequence of instructions between implementations, get the same result, excepting for non-deterministic factors. And finally, if you pass architecture test, the architectural compatibility test, ACT, you get to brand as RISC-V compatible if you are a member. And finally, I just want to flash up some of the supporting documents. So the profiles policy document is here, and we've written all the stuff down in prose that you saw there on the slides. The second one is the profiles spreadsheet, where we actually have all of the profiles for the different years, and with all the extensions as rows. And then it says what their disposition is, which is mandatory or supported, unsupported, not implemented, or at that time, not ratified, or not applicable. And then finally, we're working on a prose document that is in GitHub in the standard locations for under profiles. And it is very preliminary. All of them are very preliminary. They're considered at discussion state, so they haven't even reached development state yet. As soon as they do, we will bring in a broader set of audience to help us there. So this is very exciting. It helps us stop fragmentation. It enables people to share things more reliably and significantly. And thank you very much. Back to you, Davide.
Thank you, Mark. And now let's hear from Jerome.
Thank you, Davide. Now let's have a small glimpse at our core roadmap and how they can map to the RISC-V profile. I understand that the name of our course is quite complex, so here is the reading guide. This is the example of our first core, the CV32E40P. CV means Core-V, is the brand name of OpenHW course. 32 is the size of the course, so 32 or 64. E means embedded, and there is also an application class. Then the 2 digits, the first digit is the pipeline length. 4 obviously means 4 levels of pipeline. The 0 is the version, and the P denotes some special cases. You will also need to know that we use the TRL ladder to express the maturity of our course. So the low TRL start with research, and the highest TRL mean production, full production. There are three sweet spots with our cores. It's TRL3, it's a proof of concept. TRL4 is a prototype, and TRL5 is a fully verified core that is ready to be used in an industrial application. With TRL6 and 7, you get cores that are silicon proven and that can be demonstrated on the field. This will be needed to understand our roadmap. So let's start the roadmap at the bottom end of this slide with the CV32 in20 core. This is a 2 stages of pipeline core. It's inherited from ETH Zurich 0 RISC-V, then IBEX core. It's a small core for very well suited for microcontroller, and it targets industrial application. Then we have the E4 range of core. It started with the CV32E40P. This is the RISC-V core that was donated by ETH Zurich to the OpenHW Group. It has undergone verification for its RV32I, M, and C extensions. It's already available and it's ready to integrate in industrial projects. There is a V2 version of the core which will add verifications of the PULP and FPU extensions. It will also target industrial application with its TRL5. There are 2 derivatives. The CV32E40S will add security extensions to the 40P core, and the 40X will add an extension interface so that you can add custom opcodes to add instructions to the core, so as a coprocessor. There is a special case in this roadmap. It's the CV32E41P core. It's a proof of concept core that reuses CV32E40P to demonstrate the feasibility and the viability of the ZF in X and ZCE extension that Tariq will introduce in a few minutes. And then jumping to the application side, you have the CV-A6 family, which includes 2 cores, the CV32A6 and the 64A6 cores, which support Linux, target ASIC and FPGA. And obviously, you have a 32 and the 64-bit versions of this core. Worth to mention is that they share the same RTL code base, and this is they inherit from the Ariane core from ETH Zurich. And the last addition to this roadmap is the CV32A5 core. So it's the Tiger core from Simon Fraser University. It's a prototyping project, and it targets FPGA. And let's try mapping this core to RISC-V profiles. I will just add a disclaimer. This is the information is provided without any warranty. This is a tentative mapping because mapping a core is proved to be quite a complex exercise. So take this information with a little pinch of salt. So starting from the top of the list, the CV64A6 likely qualifies as a RVA20 USM 64-bit core. So A for application and 20 for 2020. US and M, these are the privilege modes that are supported, and 64-bit is quite obvious. This is a 64-bit core. The next core, CV32A6, likely qualify for RVM20 USM32. From what I understood, the RVA profiles do not support 32-bit cores. So that's why it qualifies as an RVM core, but worth to mention, it supports Linux. The story is almost the same for CV32A5. At full configuration, it supports RVM20 USM32. The Simon Fraser University team has planned to add more extension to this core. And then when jumping to the embedded cores, all of them qualify to the RVM20M32 family. And worth to mention is that the E40S also adds the user mode level. That's all for the formal presentation. Thanks for listening. I'm sure you will have tons of questions. Back to you, Davide.
Thank you, Jerome. And now let's welcome Tariq.
Thanks, Davide. So I'm going to talk to you today about RISC-V code size and what we're doing to try and reduce it. So I'm the chair of the code size reduction task group. What we've found is that RISC-V code size is larger than for other mature embedded architectures, partially because it's newer, so there's been less compiler development, but also because we need to add instructions. We need to enrich the ISA to make it better. So within Huawei, we've seen our IoT code increase by 15%, moving it to RISC-V. So what I'm proposing here is a set of 3 extensions as subsets of ZCE. There are more instructions, which achieves about a 15.25% reduction on the IoT code. Overall, about 13% across the benchmark suite, and some of the benchmarks are listed there. So what we're proposing is to add more 16-bit encodings, and you can see the 3 sub-extensions which are proposed, ZCE, E, B, and S, and the link is there on GitHub to the code size reduction page. So the first one, ZCE is suitable for all cores, so you can use it on high-performance cores. It's very simple. The functionality is either already in the ALU if you've implemented parts of the B extension, or is very simple to add. So it's a set of 6 encodings. Most of them are sign and 0 extension, but there's also compressed multiply, which is particularly useful for a range of algorithms, including audio codecs. So overall, we find that the weighted average code size saving is about 0.35% for all of the instructions. And the highest benefit was PicoJPEG from MPEG, compiled with GCC 10, which achieved a 3.85% reduction in code size. So ZCEB, again, these are very simple instructions, but they're sharing the encodings for the D extension, the 16-bit encodings. So the floating point load double stack pointer, relative, and the 2 stores. So this means that if you're using them, you can't use the D extension. You can use the D in X, which is the double precision floating point using the integer registers. And in the future, RISC-V International may allow a subset of D with these instructions instead of those compressed D encodings. So the instructions are very simple: load, store, byte, half, and the loads are unsigned and signed. We consider stack pointer relative versions. Benefits were low, but better for stores, so maybe in the future. Overall, average saving was 2.43%, and mbent statemate saved 6.6%, which is very good for those 6 instructions. So the more interesting instructions are in ZCES, S for sequenced. So here we sort of push the boundary a bit and do more interesting things, which save more code size. So the first instruction, C.MVA01S07. So just to explain it, it's a C.MV, it's a compressed move instruction. It moves into the register pair A0 to A1, 2 individually indexed registers from S0 to S7 using ABI names to reduce encoding space. So this is used for setting up function arguments, and you'll find you'll need one of these before almost every function call. So executing it requires a 2-step sequence, or you could implement a paired write port. Obviously the 2-step sequence has worse performance, but you need a sequence for the push-pop instructions later. So there's no 32-bit equivalent of this instruction. Overall, it saves as much as ZCEE on average, and on one particular spec CPU benchmark, it saved 1.46%, which is very good for a single instruction. Okay, so the next one is table jump, which is a form of dictionary compression. So what you do is you find your 256 most frequently called functions, you put the addresses of the functions in a table in memory, you set the table JAL vec CSR to be the base of that table, and then you use the 16-bit encodings, which include an index into the table, to call your function. So if you call indices 0 to 63, you don't link, so that's c.tblj, and 64 to 255, the rest of them. If you call indexes 64 to 255, then you link to RA, so that's the rest of the table. So most of the table links to RA. So what you're doing is you're replacing 32 or 64-bit code sequences with a 16-bit reference. And you get a 16-bit reference wherever the destination is in memory. So currently RISC-V code will give you a 64-bit sequence to call a function if it's more than a megabyte away, and a 32 bits if it's nearer. There are no 32-bit equivalents of these instructions. The average benefit's about 2.5%, but the LC3 plus audio codec in fixed point mode achieved a massive 9.3%. And finally, all other embedded architectures have some kind of push and pop. So this is the RISC-V version. So we're rolling up function prologue and epilogue sequences into single 16-bit encodings. So just some examples here, c.push is going to push registers S0 to S1. That list could be longer. It could go all the way up to S11. And it's then going to move A0 and A1 into S0 and S1, because what typically happens is once you've saved your saved registers, you move the argument registers in, and then you set up the argument registers for the next call using a c.mva 01s07 call instruction, and then you adjust the stack pointer by 64. And for your function epilogue, you call a popret. So again, you specify the register list. In this case, I have an optional argument to move 0 into A0 as the return value. You adjust the stack pointer, and then you return from the function. And there's also a cut down version, c.pop, used for TAL calling, which doesn't ret and doesn't have the return value option. 32-bit equivalents are proposed but may not be available when we freeze the spec. So overall, the average benefit relative to msave restore is 7.79%, which is enormous. And one mbench benchmark even saved 36%, as it's tiny, and the msave restore routines are actually very large. And so the E41P, which is based on the CV32E40P, we're implementing the extensions we just listed and other instructions in ZCE, because I haven't listed all of them. And we're also implementing the ZFNX extension. So it will be available as a TRL3 prototype reference design. And that's all from me. Thanks, and back to you, Davide.
Welcome back, guys. I hope you liked the video we just saw. So let's also welcome back Jerome, Tariq, and Mark. And so here we are to answer your questions. Maybe I have the first one for Mark, which is, how did you decide to divide all the RISC-V profiles in that specific group of ISA extensions? Was it like a study on the application side, or more into the hardware side, a mix of that? I think you're muted, Mark, sorry.
Thank you. I'm not sure what the question is actually, because the profiles for 2020 were things that were ratified in 2019, and the profiles for 2022 also are more reactive. They're things that were underway that we're going to get actually ratified this year. We have 16 specifications, most of them in privilege, but there's big ones in unpriv, like vector and cryptoscalar and bitmap. So the list of extensions that go into the profiles is happenstance for these years. The intent of the steering committee for RISC-V is to get more top-down, strategic-oriented, and have us work on the things that are important for the community, as opposed to the things that we happen to have in flight. Now, we do have a backlog to clean up. So once you have the set of extensions that are there, the next thing you have to do is decide how you're going to break up the profiles, and I explained that in the talk about, you know, sort of the year of the profile, the type of the profile, the mode, and the 32-bit versus 64-bit. So those are all, it's a cross product. And then it came down to deciding what belongs in what. And there are some high-level philosophies in place. The folks who are doing M profiles want as little mandatory as possible. So in particular, the great example is M. You don't see M required in the M profile. Sorry, M's now used 3 places. M being multiply divide is not required in the microcontroller bare bones profile. By the way, I'm trying to get them to change the microcontroller letter because it's not official yet. And having 3 M's is a little more confusing than 2 M's. So we're going to try to get it down to 2. But M, for example, isn't there because nobody wants to divide. You're going to see very soon after the new year, we're going to have a fast track for ZM mul, which will just be the multiply by itself. So that's an example of breaking it down. So the reason, the philosophy behind that is really driving it, which is don't require the SoC, IoT, embedded, low, small footprint guys to, mandatorily include stuff. On the application, the rich OS profile, that's driven a lot by, our expectations of what applications need. So things like bit manipulation, as you could see, are going to be mandatory in that profile for RVA22. But things like vector will be optional, supported optional, because not all machines will have a vector. So I think they just try to use their common sense about what really should be there. If people don't have those instructions yet, it just means that they'll be compatible with an older profile. And of course, the oldest one is RVI20, and that's the easiest one to be compatible with. So if you could ask the person asking the question if I answered it, because if not, I'll be glad to adjust.
You actually did answer the question because the answer was from me. So
okay, good.
Yeah.
Sorry, long-winded.
Yeah, it's really a curiosity about the high-level philosophy and the common sense part. Okay, thanks a lot. And actually, we also have a question from the attendees, which is, which core do you propose for long-term FPGA use? Something to migrate from microblaze or NEOS towards? So from microblaze or NEOS towards which core or which RISC-V profiles? I guess this is which core. So I let Jerome answer the question.
Yes, the question is about which core, because the profiles do not address the underlying technology. So you could see in the roadmap that there are 2 cores targeting FPGA technologies, the CVA6 and CVA5. CVA6 targets TRL5, so industrial application, and the CV32A6, more specifically, so the 32-bit version targets FPGA optimization. There are works ongoing for this optimization, and there will be a continuum between the FPGA and the ASIC version. And so when there are already some stuff available on our GitHub, and while the project is ongoing, and we target an industrial version in the future. On the CVA5, So it's a core from Simon Fraser University. In the current project, they target a prototype, so TRL4 in our technical readiness ladder. And so I would say they can be used for, this core can be used for research, but I don't think it will be suitable in the current definition for industrial adoption. And the good news is that the OpenHW cores are not proprietary, so you can use them on any technology, FPGA technology you prefer.
Thank you, Jerome. Maybe you want to say something about the optimization you're doing for the CVA6 for not making it a soft core, but let's say reducing the gap between an ASIC only core to a soft core good enough.
We can say that we target a soft core. So at the moment we are trying to optimize its performance, and internally we've achieved a 50% increase on frequency by solving a few, by improving the PMP-MMU instruction cache interfaces, but it's internal. It's not yet. It's very fresh, and it's not yet available on our repository.
Thank you, Jerome. So maybe I also have another question, this time for Tariq, as we are discussing area and performance. Do you know, Tariq, if you have preliminary numbers or an estimation, what does having ZTE cost in terms of power and area, or even just area, if it is that preliminary, in a, let's say, RVI 20-like core? So using the profile one to say, it's a microcontroller core. It's meant for bare metal or FreeRTOS or real-time operating system. We are not targeting application scenario. Has it a lot of benefits in terms of area in the core? And of course, you already showed the saving area in the memory. But how much does it cost in the core?
Well, I don't have any figures yet, but from the 3 extensions, ZTE E pretty much maps onto existing hardware. So it's just a change in the decoder, so it's essentially free. ZTE B is the same, it maps onto existing hardware. ZTE S is the more interesting one. So you do need to implement a state machine to generate a sequence of instructions. I don't expect that to be large at all. And also, if you think about executing C code, you're spending an awful lot of your time executing the function prologues and epilogues. So actually, it will be spending an awful lot of its time just running the sequences, the push-pop sequences. I think I don't have any figures for it, but I suspect something like 10 to 20% of the execution time, obviously very code dependent, and it's just a guess, would be spent just doing push and pop. And in all that time, it's not instruction fetching. So I would expect there to be a considerable power benefit. And also the fact that it's spending so much time executing those sequences, I think gives good opportunity for optimizing them really, really well in a core, in an implementation, to get the power and performance really, really good. Because, as I say, it will spend a lot of its time executing just those 2 instructions.
As you mentioned, the fetch instructions, maybe do you also have some ideas about how this translates in RV like application ones? I mean, where they usually have cache. I guess you increase you reduce the cache miss as well. So also, how do you see these instructions in the application scenario? Will they also benefit as much as the embedded ones, or not? For sure, the ones for free. And
yeah, so the application core question is obviously a different one. So the first two extensions are the same. They're basically free. The sequencer in order core, in order application core, I don't think would be too much of a problem. In an out of order core, I think it gets more challenging. So it's not a problem I've thought all the way through. So it's very much focused on embedded cores at the moment. But if they are implemented, they will greatly improve the cache utilization, because push and pop on their own frequently reduce the code size by about 9%. So, you know, you get a 9% bigger cache effectively, and who wouldn't want that? And again, that's good for power as well. But yeah, there'll be some challenges to work through there to make it work in an out of order machine, I think.
Thank you. Do you guys have questions also for Mark, for us as for the three of us?
I have a question for Mark, if we don't have any more questions in the chat box. Mark, I went through the spreadsheet and it was not very clear for me if we can have RVA, if we can have 32-bit cores qualifying for RVA profiles, so the application profiles, because I could read that RVI 32 is only applicable to RVM and RVI profiles, but in another line I could read that RVI 32, so the 32-bit base RISC-V extension was mandatory for RVA cores.
Yeah, so you know, RVI was intended to just deal with the first 47 with the basics it takes to boot the machine. You know, RVM is kind of very bare metal. So even if you're running Linux, you could be compliant with RVM, right? You don't have to do something. RVA is intending to sort of put more constraints on. So we have similar things in the field. You know, the flags for GCC and LLVM could be like dash RVA, you know, 22U64. You know, as I said in my talk, we only started with 64 with RVA because it looked like most of the sophisticated rich OS things were in 64-bit. But also, as I said in there, if there's big demand for 32, we can do that. They just wanted to like get something out the door. So, I mean, as you know, you're part of the group. You understand that there's limited resources for everything from, you know, architecture tests to architectural review to other things. And so, you know, we worked very hard to set priorities this year and join together and get the things that were most important. So the board said the big four. The big four were vector, cryptoscaler, bitmanip, and a bunch of the priv stuff, including hypervisor. Right after that, the next highest priority is profiles. And so we're trying to get something out the door probably in Q1, ratified in Q1. Because everybody's working on the big four and the sort of the 16 separate specs, including ZF and X. Thank you, Tariq. You know, for Summit. So we're just trying to set priorities and accomplish some things and not like do poorly on everything. So it's not saying that we won't do an RVA 32. It's saying right now we're not doing RVA 32 because most people working in the RVA world are doing 64-bit, and there is the opportunity to be compatible with the RVM or RVI profiles. Does that answer your question, Jerome?
I think so, yes.
Yeah, sometimes with these, you know, this stuff's evolving, folks, just so everybody knows. This is new for us, right? And we're not going to get everything right. So if you see something wrong, help us make it better. We're a community and we need your help to do that. We're not proud. We'll take as much help as we can get, and as much advice. I just can't guarantee you we're going to take your advice. There's a lot of people with different opinions, and you know, at some point you got to make a decision. We are not a consensus organization. We are a majority positive organization at the direction of the board, because we weren't making progress, and we needed to make sure that we had a way to do that.
Thank you, Mark.
Sure. Boy, everybody's quiet.
Yeah.
You know, it's a lot better when you have a beer in front of you and you're sitting next to somebody. But when it's over Zoom, it's like, you know, it's a little more stonewall. But we always welcome questions even after the podcast is done.
I agree with you, Mark.
Mate, how about an intro to what we can expect from the RISC-V Summit next month, Mark?
Oh, absolutely. So, you know, RISC-V Summit is our first, you know, is our big get together. And this is our first one post COVID, you know, that we're trying to do in person, and hopefully everything holds. The U.S. has, you know, removed the travel blockades if you have a, you know, proof of vaccination. There will be proof of vaccination required for Summit. So if you're unwilling to do that, then you really have to do it virtually. We will have a virtual interface. But I will tell you, I just attended the Linux Member Summit, and it was the first in-person conference I did since COVID. And boy, it makes a difference when you're sitting next to somebody. You know, people who, you know, we've had misunderstandings with or whatever over time. It's easy to clear those things up when you see that person sitting next to you, and you can see their body language and their tone of voice, and you're sharing a, you know, like they're having a meal at the same time as you. So I think those things are primal. So you're going to see a lot of that at you know, at the RISC-V Summit. And I would say, to me, the most important thing is to see people. The next important thing is to understand, you know, what we did over the last year, because the gentlemen who are, you know, on the conference here made big contributions, and there's a lot of work that we got done. We produced 0 specs in 2020, and there's 16 going out in 2021, and there's a bunch on deck for the first half of 2022. So we're very excited about that. So understanding that, understanding the sort of the state of RISC-V. You know, we built a scalable organization. I felt very grateful that we didn't break the organization as we were building it. There was no governance. There was no scalable structure. We now have that. Software, for example, went from 1 group to 15 groups in a year. And so we're very excited about that. We established special interest groups in a different way than before. They are the continuity. They are responsible for strategy, gaps, and prioritization. And then task groups come in and do little things and try to get things done. We're trying not to do boil the ocean task groups in the future. And you're going to see that message come out at Summit quite a bit. And then finally, you're going to see a raft of technical talks that have been submitted. Some of them researchy, some of them, you know, practical that people are doing right now. Some of them related to product that are being put out. But I will tell you, you may not know this, but in 2021, there will be in excess of 2 billion RISC-V cores deployed in the world. We were told by Alibaba last week that they alone are shipping 1.2 billion cores in 2021. We know that there are earbud manufacturers in China who are shipping 50 million RISC-V cores a month. We know that there are home automation SoCs, Espressif, TE-Link, that are shipping you know, a huge number of RISC-V cores. And both Alibaba and Espressif are going to be open sourcing their cores. So it's a very big growth in the open source community. We're in this together. You know, people are realizing that, you know, again, this duplication piece is killing the world. I mean, this is a human species problem. This is not a RISC-V problem. It's not an America problem. It's everywhere, right? It's a real problem that we're wasting human resources on duplication. instead of innovation. And we really want people spending their time on innovation. I think that we all know that we have the building blocks in place to do extraordinary things with technology. And we now have to make sure that people are able to do that instead of having to go ahead and repeat what everybody's done 100 times before. I think there's also power in numbers. You know, as you start seeing more things come out in RISC-V, you're going to see more people say, oh, they could do it, so now I can do it. So you're going to see that momentum there as well. There's at least a half a dozen development boards out there which are fueling innovation and fueling use. RISC-V International is trying to get 1,000 of them out itself, not including the vendors, out to distros, early adopters, and academia by June of 2022. The world parts shortage slowed that down. We had hoped to do that by December. So you're going to see all that at RISC-V. You're going to see some extraordinary people, you know, people like, you know, Krista and Dave Patterson and Dave Ditzel and, you know, a bunch of other folks who are industry luminaries showing up and participating. And I think that, you know, I think the big takeaway is, you know, get involved, you know, do what you need to do. I mean, the reason why RISC-V is successful is because you can customize, right? You're flexible. You don't have to do everything. And especially if you're in the IoT embedded space, it's like, you know, do what you need to do. You're not doing a general purpose computer. You know, as you go up the stack, then you're more interested in general purpose things. But, you know, a lot of people have just taken the RISC-V core and just run with it. That's what we want. I mean, that's exciting. And again, as more people deploy, you're going to see more momentum. But, you know, we have extraordinary charts calling for in excess of 80 billion cores by 2025 deployed at RISC-V. And I have no doubt about that. We know it's everywhere from, I like to say, it's everywhere from soldering irons to supercomputers. Pine 64 did a soldering iron. I have it here somewhere. Here it is. I'll show you guys. So this is the Pine 64 RISC-V soldering iron. USB rechargeable, and then, you know, BSE, you know, the folks in Europe are going crazy with building stuff. We've given a lot of boards to John Davis at BSE, and so it's a very exciting time. Does that sort of answer the question? I think it was Tariq.
It was Tariq's question. Was it?
Yes, it definitely does. And also, talking about very large volumes, it sort of makes the code size thing much more important as well, because the vast majority of those volumes are going to be the little embedded cores.
Yeah, so, I will tell you, I want to thank Tariq because he's been put through the ringer on process.
and continue to be so.
and he's been very kind in how he's reacted to it, and we're working to try to. I mean, look, as you can imagine, the 16-bit opcode space is precious, right? So people look 10 times to make sure we're not wasting an opcode. And so, you know, the one that's been blessed is push pop is very clear. It's 5 to 15%, depending on what the workload is. It's a no-brainer, right? When you start talking about things that are sub 1%, you have to make a conscious decision as to, do I want to spend that opcode doing this, or do I want to save it for the future for something that's going to actually reap bigger rewards? And Tariq's in the middle of those discussions with, you know, people like Krista and Andrew and John Hauser. So, thank you.
Yeah, and also the amount of when I started the code size, it's because we recompiled for RISC-V and the code didn't fit in the flash anymore. If you think about the impact on future flash prices just based on what ends up in my extension,
yeah,
I think there's a very strong correlation between the two.
No, I agree with you. And the one thing I'll encourage your audience, you know, I still see there's a lot of attendees still on. One thing I'll encourage your audience is get a hold of Tariq and make sure that your workload is represented, because the thing I got afraid of the most, and I brought this up with Tariq, I mean, this isn't a surprise, is that, you know, look, people talk about benchmarks, MBench and spec and, you know, MLPerf and blah, 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 blah. And they're all very nice. Look, I was at MIPS in the 80s when spec started, and we were trying to get away from Drystone, and Drystone's used very heavily still. The only thing that matters is your application and your workload. right? You can talk about contrived stuff all you want, and you hope that they're representative of the real world, but the only thing that's representative of the real world is your application and your work and your data set. And so if you haven't, and you're interested in this, please get a hold of Tariq. He's worked with a person who started as an intern and now I think is an employee, did a spectacular job of putting a framework together to do some static analysis on the impacts. And we welcome, I hold them up as the poster child for other groups saying, we want real data. We want a means test that we should be putting instructions in and not, look, sometimes there's functionality you got to have that there's no proof other than like you need to be able to do debugging, right? But when you're talking about something like code size reduction, or you're talking about something like vector, you want to see the impact on real applications. And so, I encourage you all to engage. If you're not a member, you become a member for basically for free as an individual. The strategic memberships are pretty cheap, but get involved, go to the meetings, get involved with this process, because the only way this gets good is by you guys. I don't dictate anything. I'm the CTO. The only thing I do is I bring things into the light and try to get into closure, right? And so this is driven by the community. So your involvement is definitely important. And I meet with Rick O'Connor from OpenHW, and I meet with Rob Maines from Chips Alliance every month. And we work together to try to make sure that the whole community and the whole ecosystem from all the way from the bottom to the top, including implementation dependent stuff, is robust. And we have to make sure it's there in order for RISC-V to be successful. And frankly, again, I think it's an optimization around the species. We break down barriers between countries, between companies, between people and cultures and time zones. And we work very hard to be egalitarian and to try to move the state of the art forward. When we enter the room, I guarantee you, it's all about being good engineers and producing good product.
Thank you, Mark and Tariq, for the very fruitful discussion. I think we have the last 2 minutes. Maybe we can answer in the fly in 1 minute the last question that has been typed just during Mark's talk, and it is a general question, and that is, why is there no news of a RISC-V MCU microcontroller from popular companies like NXP, ST, Microchip, or Texas Instrument? Maybe just on the fly, what can we say?
Yeah, so sorry, the dogs are barking, but
no problem.
Yes, they are. They are doing. Microchip for sure, NXP for sure. The problem is, since we are not like other companies that are proprietary that charge per core or per license or per product, we don't get those numbers. So we rely on a couple of things. One is members telling us things. So we tell everybody, look, we hold no secrets. Don't tell us anything that's a secret. But anything that's public, go ahead and tell us, and we'll help amplify it. But I'll encourage everybody on the phone to encourage their friends. We have RISC-V Exchange, which is free advertisement. You can put any product up there, service, FPGA, chip, software, end product, servers, whatever. You can put up there and advertise and let everybody know what's going on. But other than that, we rely on the same thing you guys rely on, Semico, right? Those kind of analysts tell us, where things are being used, because they do the surveys all the time. This is frustrating, I will tell you, for us. And so the more information people can share, the better. But we aren't the holders of that information, and therefore, if it's not out in the public or people aren't advertising it successfully, we often don't know about it. I heard anecdotally about these earbud manufacturers through Penn Lee, who's a marketing person at Sci-Fi. And it's not a secret. He just said, look, there's these 2 earbud manufacturers and they're producing a lot of stuff. So that's just an example of a huge volume that, that people just, don't even know about, because RISC-V allows that. You don't have to say Intel inside, right?
Indeed. Thanks a lot, Mark. And with this, I think we are arrived at the time. We have to wrap up and say bye to everyone. Thanks a lot for everyone for attending. Thanks, Jerome, Tariq, and Mark. And see you at the next episode of the OpenHW TV.
Thank you.
Bye.
Goodbye.